Okay, today we'll be starting section 12.3. It's actually titled 12.3 in your notes, but it doesn't actually go along with 12.3 in the book. So heads up on that. If you're going to use your book as a resource, there's nothing there in 12.3. Okay? All right, so the title is continuity and discontinuity. Here's what it means for a function to be continuous. Go ahead and write this in. The graph does not have vertical asymptotes, holes, or any breaks. The graph doesn't have vertical asymptotes, holes, or breaks. And usually when it's continuous, you can always kind of draw the graph, right, without lifting up your pen or pencil. So that's another way to make sure it's continuous, right? If you pick it up to continue drawing it, it's because it's maybe discontinuous. Okay, so discontinuity. We'll describe discontinuity by the x value where the function is undefined. Okay, so it's not usually enough to say, yeah, it's discontinuous. Well, if you're going to say it's discontinuous, we need to study the x value, sometimes called the a value in the definitions, where the function is undefined. Okay, parentheses here, I put the location of the break in the graph. All right, so here's the three criteria that have to be met for a function to be considered continuous. A function f is continuous at, it's the letter a, or number a, okay? So I'm going to put that in quotations if it helps to, it's not really at right? It's at a. Anyways, here's the three criteria. The function must be defined at a, okay, so that it's in the domain of f, so that f of a is a real number when we plug it in. We shouldn't have like divided by 0 or something like that, or square root of a negative. All right. The limit of the function, as x approaches a, it does exist, right? We don't have a does not exist scenario. It needs to exist to be continuous at that spot. And then when you plug in a into the function, whatever number you get, let's just say it's 5, it's going to be the same as the limit of the function. As x approaches a, we'll get the same thing. All right, because remember with limits, they should be approaching the same number anyways, and it has to be defined at that spot. You can't have like an opening or an open circle or an asymptote there. Okay, so those are the three things that must happen. Okay, so let's take a look at the first one here. Find the numbers at which f is continuous. At which numbers is f discontinuous? So usually when it's discontinuous, we're going to use one of these three options here to justify it. So you may want to add that to your directions. If it is going to be discontinuous, we'll justify it by the means above. All right, so here we go. First example. Find the numbers at which f is continuous. So if they give you a graph to look at, it should be pretty obvious, right? Where am I picking up my pencil to draw this? Right here. I have to pick it up and then put it back down over here. So it's discontinuous where this vertical asymptote is happening. So to answer the first question, find the numbers at which this function is continuous. Let's just make a statement like this. It's continuous everywhere except x equals -2. Or we could use interval notation too, right? You could say continuous for -infinity to -2, and then the union of -2 to infinity. That would be another way you could explain that, okay? All right, which numbers is f discontinuous? We kind of answered that there, but to justify it, here's some things that we could do. F a -2 okay. For it to be continuous, when we plug in the value a, it should be defined, right? It's not defined. We don't get a real number. So f a -2 is undefined. So that's one way we could justify it. I'm going to give you another option, or I want you to write down both. I think in a quiz, we're only going to ask for one, but maybe we may ask for more. I'll let you know, but for now, one should be good. But let's write down both. What is the limit? The limit of the function as x approaches a. Does it exist or does it not exist? Well, from the right side of -2, it's approaching positive infinity, and then the left side, it's negative infinity. It's definitely not approaching the same number, so it actually doesn't have a limit. We'd have to say this doesn't exist. All right, so another way we could justify this, that is discontinuous, is the limits of this function as x approaches -2, new pencil, does not exist. The limit of that function as x approaches -2 does not exist. It must exist to be continuous. So you might be wondering, well, is it always going to be does not exist? No. I mean, if we looked at some other random number over here, like 3, it is continuous at an x value of 3, right? If we needed to analyze that spot. Because as x approaches 3 from the left and right, it's approaching some decimal of like 1/10. So it does exist there. The function is defined at 3. And when we plug in the x value, it will be the same as the limit. All those things pass here for a bunch of values here. Okay, but we studied -2 because that's where it was discontinuous. All right. Number 2, find the numbers at which f is continuous. This just looks like some variation of y equals x cubed. This is a cubic function. It's going to be continuous for all x. These have arrows on it to show that it keeps going, right? It's just a computer program, so it's not there, but we can assume it's going to continue. So this is continuous for, I'll just put semicolon, negative infinity to positive infinity. Or you could say in words, continuous for all x. Okay, so it's kind of new, a little different. So pause for a moment and try number 3. I think you can tell that it is going to be discontinuous, but let's see how you answer these 2 questions. How can you find the numbers at which it's at which it's continuous, and then see if you can provide some type of justification for the discontinuity here. Okay, go ahead. Okay, here we go. Number 3. It's continuous except for these 2 spots. -4, it's an open circle. I gotta look kind of close to see that. All right, and it's discontinuous at -2. So here's some justifications we could use. Okay, so x equals -4, we could just say it's undefined, because really step 2, the limit does exist. As x approaches -4, it does have a limit of 1, but it only takes 1 violation for it not to be continuous. So for this one, we could use justification 1. That's why I'm hitting number 1, so we align it to that one. F at -4 is undefined. We could actually use justification number 1 for this one too. X equals -2 is undefined. Okay. Or let's take a look back at x equals -4. I couldn't use justification 2. It does exist. Okay. It's a limit of 1. But the second one, which says f at a, is that equal to the limit? So the limit we just found was 1. Does 1 equal the function identified at a? Well, f at a, I'll label this as 3. So f at a was undefined. So f at a was not equal to the limit of this function as x approaches a, is what I'm using, because this was undefined and that was 1 from our graph. You understand? Okay. So violation 3. So I'm just giving you options, one way or the other. That's how we can say it's discontinuous. Okay, for x equals -2, you could use all 3. But let's go on to at least the second one. The limit as x approaches -2 does not exist because they're approaching different y values. So the limits of f of x as x approached -2 here was equal to does not exist. And again, even if we went on to step 3, I guess those aren't technically equal. They got to be equal values, equal numbers. We're not even getting values. Okay. All right, now if they don't give us a graph, we could use our graphing calculator to peek at it if we need to, or sometimes we can just use our prior knowledge. we should know by now that this is a quadratic function degree 2. Okay, so I'm just making a note here in parentheses, pulling from our prior knowledge. This is a quadratic function. Quadratic functions always have domain of all real numbers. It's a continuous parabola. There's no asymptotes, no holes. So this is continuous for negative infinity to positive infinity. No problems here for number 4. Okay. If they gave you a linear function, you could come up with that from your prior knowledge. Even if it's a cubic function, we know those are continuous. But like I said, the other option is to throw it in your calculator. Okay, so the direction is still the same, right? Where is it continuous? If it is discontinuous, maybe we can justify it, but it wasn't discontinuous. So we got a pretty short, easy answer to number 4. Okay, about 5. Well, we'll peek at this in a moment to verify this, but you could also figure out where it's undefined by using our algebra skills. You might want to you could set this equal to 0 and solve it, or you could just kind of factor it, because if you factor it, it should be very obvious where it's going to be undefined. So by difference of squares, we know this is x plus 7, x minus 7. Okay, and now it should be pretty obvious where your points of discontinuity are. So this would be continuous, and like I said, we'll verify with the graphing calculator in just a moment, but it looks like it's going to be continuous for all x except a negative 7 and positive 7. So continuous except at x equals 7 and negative 7. Okay. Why? We could use the justification. F at negative 7 and f at 7 are both undefined. Okay, we'll take a look at the graphs too and look at the limits here in just a moment. I'm going to pause to punch that in the calculator. Okay, so if you want to verify with limits or the graphs, remember you also have the table feature you could set up, and we could take a look at x equals negative 7 at table setup, put in negative 7 there, look close. All those are options, but here's the graph, and then this is kind of confirms what we see. This is a continuous graph. Okay, I don't have to pick up my pencil to draw this, but I do right here, right? And continue here. So there's an asymptote at 7, and there's one at negative 7. Okay, confirms what we see. The limits don't exist, right? Because I'm approaching different y values at both those spots. Another way we could justify that. Okay. All right, you guys try number 6, and then I'll wrap it up on those piecewise at the bottom. Try number 6. Okay, here's your feedback. This factors to this, x minus 4 and x minus 6. So now it should be pretty obvious what numbers make this undefined and give us zeros down there, the 4 and the 6. So it's continuous besides that. So your justification could be that they're undefined there, or maybe you threw in the calculator and you checked, the limits did not exist at both of those spots. All right, I'll finish with a piecewise graph. Most of this can be done in the graphing calculator. So let you pause this at home too while you're writing this down. For most piecewise problems, the possible points of discontinuity will happen at the boundary, like the negative 4, the 2, and the 9 for these problems. Go ahead and write that down. Okay, so remember, we can use our skills of setting up a table from before to see if the limit exists and to see if it's defined. So what I do is plug in 9, right? We like to put 9 in the middle, the point of interest. And then I could do like 9.01 here, 9.02, and 8.99. Just take a look at the values as they approach that to see if the limit exists, and then see if it's defined at that spot. And then are they equal? All right, so when x is 9, I could punch it in. You're going to have to use this one. Square root of 9 is 3. 3 plus 2 is 5. So I could quickly get that without my calculator. Now, with these decimals, you're going to have to choose less than or equal to 9. So throw those in there, calculate it, write it down. And then the same thing here. Now you're going to have to use this function. Okay. You can also, if you want to get fancy with your graphing calculator, plug these in as I demonstrated before. Put the conditions there, and then you can actually view the graph and see them that they are connected. All right, here, it's square root, and then it has the linear function right there. So it is continuous at 5. I could even trace it along to play with that, and I can look at the table. Okay, so I'm getting cut off here. I'm just going to wrap it up. It is defined at 5, and then it was approaching 5, so that's why the limit exists. So put the justification down there. Okay.